Welcome everyone to the IVM seminar this week. It is my great pleasure to welcome you to the talk of Silvio Künstner. He does EPR-on-a-chip work, and I'm particularly thrilled to introduce him because he's from our group in Berlin, the Department of Klaus Lipps, where we work on materials and devices and try to use EPR to uncover defect states and current limiting processes. But so what he's going to talk about today is how we've adapted the EPR-on-a-chip device to become a submersible standalone spectrometer. And so with that, the floor is yours, Silvio.
Thank you very much, Joe, for the introduction and also for the invitation to the seminar. So my talk is called EPR-on-a-chip dipstick, and this essentially EPR-on-a-chip dipstick was developed somewhat in a project which was in a project where people from University of Stuttgart, Jens Anders Group, Alexander Schneck from Max Planck Institute for Chemical Energy Conversion, and Brucker and the Helmholtz-Zentrum Berlin Klaus Lipps groups, we had a grant, and so we developed some EPR-on-a-chip technique there. And I did my PhD, or officially I'm still doing it. I just finished writing my thesis, and will submit it we'll submit it soon. So to motivate my talk, I know this is an EPR seminar, so I don't need to tell you that EPR is a great technique and we use it to investigate paramagnetic species. However, when we think of in situ characterization or in situ measurements with EPR, usually that's quite complicated because of the current design of the EPR spectrometers. So when we, for instance, want to investigate catalytic gas-liquid phase reactions, we can do that by having a vessel where our reactions take place, and then we feed some tubing through the EPR resonator where we can essentially investigate our sample and then pump it back. And much easier, obviously, is a UV-vis probe, which we could just stick in there, or an infrared probe. Similar when we want to do electrochemistry, we usually need to confine or build somehow an electrochemical cell that fits into an EPR tube, and then we can investigate the species that are formed on the working electrode. And obviously that is these two examples are, let's say, we have their paramagnetic states in solution or on a film, and usually we have some solvents that are not so nice for our EPR spectrum or for EPR measurement, and also here's some conductive material. So, and these generally, when we talk about like commercial EPR or EPR that we usually do, we put something in a cavity resonator, and here we have a sample in the spectrometer environment. And with our, let's say, development that we've done over the last years, we actually want to reverse this and have a, let's say, an EPR probe that we can just stick into this vessel here to investigate the paramagnetic states in solution, or that we can attach to an electrode and detect paramagnetic states here. And this bottom here, this would be maybe our, this is our vision of maybe a portable EPR spectrometer, where a battery operated portable EPR spectrometer with a permanent magnet, and you can use it to detect either some pollution in some water. So in order to get from a resonator to like such a dipstick type probe, obviously we have some certain requirements, and this is what I will focus in my talk here. So first, we need obviously an EPR-on-a-chip or some EPR device, which is, let's say, small, which we can dip some into a solution, and this should be robust. Maybe we want to be able to quantify our species, so we can have like a sensor type spectrometer, or sensor, not a sensor type measurement. We want to somehow reproduce or understand the spectral shape that we see. We need to have a certain sensitivity, and I will talk about this a little and how we may be able to improve that. I will also show you like two designs of, or two prototypes of permanent magnets. And what also is important, which I will talk shortly about, is where we actually measure and how much volume we probe. So on the left-hand side, here we have this slide from resonator to oscillator. So in this, on the left-hand side, you see the cavity resonator, and at bottom you have a like a very simplified sketch of a spectrometer. We have a microwave source circulator, which is coupled to the resonator, and then the microwaves are detected by a detector, which is also going through the circulator. And here we ensure essentially unidirectional coupling of the microwave source to the resonator. So no matter what happens in the resonator, the source is somehow not affected. Here, the L, this is the inductance of this resonator, is essentially the B1 that excites the spin system, and then we essentially get a detuning from the resonator. The chip, on the other hand, we have on this chip, we have it's a miniaturized EPR spectrometer on a single microchip. We have a certain number of coils, and the coils are octagonally shaped, and they're used as a microwave source and detector at the same time. And essentially what we'd use is the inductance of a voltage controlled oscillator. And this actually is the whole EPR spectrometer that produces the microwave and where we detect. And since this is directly coupled, we have a bidirectional coupling of the microwave source. I'll talk about now how the principle works. So when we start with a micro resonator with inductance and a capacitance, and that has a really relatively low quality factor, which you can see here, the stored energy versus frequency, and we add an active pumped circuit to that. This is a cross-coupled transistor pair, and this acts as a negative resistance, and essentially at each cycle it replenishes the energy lost in this micro resonator, and then we get from a resonator to an oscillator, and this would be the stored energy versus frequency. And when we replace this fixed capacitance by a variable one, so by a varactor, we can actually sweep the frequency very easily. On the right-hand side, you can see how such a chip looks like. You can see the octagonal coil with a diameter of about 200 micrometer. We put this chip on a printed circuit board with some readout electronics and frequency control, or phase control to be exact. We have an RF generator, which we use as a reference. So we essentially, when we sweep the reference, the RF frequency, we sweep the frequency of the chip. We have a power supply that powers the board and defines B1, and depending on what we use, we have a lock-in amplifier or digitizer to record our signal. And to put this into an electromagnet, but since we can sweep the frequency, obviously we could also use a permanent magnet. But however, in my in all experiments I show, I use an electromagnet from Bruker, which has a relatively good homogeneity. How do we measure the EPR signal? So essentially we put the sample in the coil or on the coil, and when we then sweep the field, when we hit the resonance, the oscillator frequency is changed. That would be this is what we would call dispersion signal, and this is dispersion, or sorry, this is what we call FM signal, and that is a dispersion-like signal. And when we hit when we hit resonance, also the amplitude of the oscillation changes, and that is what we call AM signal. And this is absorption-like. These are, yeah, I'll talk about this a little later. Okay, so we have this chip now, and we tested a little bit how we can do this, how can we achieve actually a stable spectrometer. And we built a dipstick prototype, and we encapsulated the chip with a Parylene C coating. It's a 10 micrometer thick film of Parylene C, which is essentially on the chip. Actually, you can see it here. And then this coating is so stable that we can detect the tempole in water that you can see here in the speaker then we can detect this in solution. So essentially, we have our EPR spectrometer, which is now here, our chip, and we have a beaker with a solution, and put this into the electromagnet. When we and we have this spectrometer has a frequency sweep range from 12.8 to 14.4 gigahertz, and the sensitive volume is about 1 nanoliter. I will show you later how we determined that sensitive volume. Here you see the spectrum of the FM spectrum, so dispersion-like spectrum, first derivative dispersion-like spectrum of a 1 millimole tempole in water solution. And from this spectrum, we can estimate the concentration sensitivity, and that is about 3 micromole per Gaussian squared hertz. Obviously, this is much lower than that of cavity resonators because of the low sensitive volume that we have. This is a design, let's say, principle. When we have a small volume, then our absolute sensitivity may be good, but our concentration sensitivity will be not good will not be very well or very good. When we calculate the number of spins present in this in the sensitive volume with this estimated concentration sensitivity, we get something like 10 to the 9 spins. And that is actually the same number we get when we use just a small grain of BDPA or DPPH. So that means it seems that water doesn't hurt so much in sensitivity wise, because usually when you have a resonator or a cavity resonator, the EPR signal depends on Q, and when you use water as solvent, then Q usually degrades considerably, but we don't really see that. So we determined this concentration sensitivity from a 1 millimole tempole solution, which is obviously easy to do, but let's look at the useful concentration sensitivity, I call it. So can we actually see like 3 micromole per Gaussian squared hertz? And here's the measurement of a 10 micromole tempole in water solution. And you can see after lots of averaging, after 6.5 hours, we see with, I don't know, maybe an SNR of 3, the 3 lines that you would expect. So yes, this number is real. However, it takes a lot of time. And so here, to summarize, we have this EPR-on-a-chip dipstick. It works nicely, and it's stable in aqueous solutions. Now, a few things about field and frequency domain spectra, because I told you already we can in principle use a permanent magnet, and so far I showed you only the field data, and here we see data from a 10 millimole tempole in water solution, and this is there are 2 spectra laid over each other. One's a field frequency sweep in black, and a field sweep in orange dashed lines, and they're perfectly overlapping with similar signal to noise. And this is the FM signal, so the dispersion-like signal, and the AM signal, the absorption-like signal, is this is probably more familiar to you. Is mainly the absorption signal. So the absorption signal is proportional to the quality factor of this coil, which is maybe 10 or 15 or so times the imaginary part of the magnetic susceptibility minus the real part. So that would be dispersion. So that is essentially depending on the quality factor. This is mainly absorption. And that is all first order approximation, because it's this getting proper estimation or approximations for the measured signal is actually quite complicated, because it's the coupling of the microwave source, so the chip, and the spin system is bidirectional. So each time we excite the spins, they essentially return some signal back, and this changes the oscillator, and then it's it's not so simple. However, since we can essentially sweep the frequency and call also in this electromagnet, we can sweep the field, we can do something that is usually only that is only possible at high fields and high frequencies, and that is called frequency domain EPR, or I call it here low field frequency domain EPR because we do it at 500 millitesla and not at like 10 Tesla or so. And the idea of these frequency domain EPRs that we essentially do microwave frequency sweeps at different magnetic fields. And if you have an interesting spin system, which is not only Zeeman and hyperfine interaction, then you can nicely plot the spin Hamiltonian on this in this map. Here we obviously see only Zeeman splitting, which is linearly increasing with a magnetic field, and the 3 lines from the hyperfine splitting, and also in FM and AM. Okay, so far I showed you it's our chip, it's stable in water, we can do field and frequency domain, they are equivalent somehow. And now and I showed you also that we think that we don't really suffer from the water, and actually we investigated this a little further by using different solvents. And we used also a tempo sample, and this is dissolved in once in ethanol, pure ethanol, and once in DI water. And when we put these samples in a resonator-based, or in a commercial spectrometer and measure, we get these spectra. So the water has a higher signal amplitude and a narrow line width, and the ethanol is a little wider. Obviously, the Q of the water sample is lower than that of ethanol because of the higher dielectric constant. And when we investigate the same sample with a chip, here you see the AM spectrum, so the absorption-like spectrum. You see it, they look very rather similar here in the frequency sweep, and similar, and also the FM signal, which is shown here on the right. We essentially were at first a little bit puzzled why the ethanol signal is so much lower than the water signal, but I found but when we like doubly integrate that and get the signal intensity, we find that the samples are have the same concentration of tempole, and everything is okay. And I actually have found in literature, I found spectra of similar samples, and they also showed this broadening. We simulated this spectrum with easy spin, essentially with isotropic hyperfine coupling and convolutional Gaussian and Lorentzian broadening, and we can simulate all spectra with the same set of parameters. And this would be here in the left in this column for water, and this for ethanol. However, there's one thing that is actually a little, or that surprised us a little. So when we look at the peak-to-peak amplitude of the water versus the ethanol, the ratio is approximately 3, and here it's 4 and 5. And when we think of why or how our signal is affected, we have our resonator Q, which is essentially defined as 2 pi times the energy stored in the resonator divided by the energy dissipated per cycle. So in the resonator base, we have essentially we increase the denominator when we use water instead of ethanol. So our Q is lower, as we can see here also from the numbers. And when we take the ratio of the Q factor, when we normalize these measurements as if they would be measured at the same Q factor, we arrive also at the same factor of 5 approximately as we observe here in the chip. So maybe this could be that with the chip, essentially, we also have the energy dissipated per cycle is larger, but as we have this oscillator, maybe the energy stored can somehow compensate for that. So it seems that DPR is sensitive to the changes in the dielectric constant, which would be quite cool. So now I'll come to the test of the robustness, and we collaborated with Peter Fischer from Fraunhofer ICT, and this person is studying vanadium redox flow batteries, and these redox flow batteries essentially utilize vanadium or 4 oxidation states of vanadium to store electricity in chemical bonds. And there's a few nice or a few advantages compared to other batteries of these vanadium redox flow batteries, because the size, the power, and the capacity can be independently scaled. So essentially, when you see here this sketch of the vanadium redox flow battery, we have an electrochemical cell which is divided by an ion selective membrane, and then here essentially the electrochemistry takes place, and we have catholyte and anolyte tanks which can be scaled as much as you want. So the capacity here is defined by the volume of the electrolyte, and the power is essentially by the number of cells, is defined by the number of cells. When we and here you can see some pictures of actually Peter standing in front of these catholyte and anolyte tanks. They're actually quite huge, and this is a stack of batteries. So in this battery, when these are used on the anolyte side, vanadium 2 3 is converted to vanadium 2, while on the catholyte side, vanadium 4 plus is converted to vanadium 5 plus. And when we the idea that we have or had is we could actually, since vanadium 4 plus and vanadium 2 plus is EPR active, and vanadium 5 plus is EPR not active, and 3 plus is depends, we can actually use this to monitor the state of charge, because that is sometimes difficult here. And these vanadium reactions take place in a mid-concentrated aqueous sulfuric acid with a concentration of 2 moles, so that's actually rather acidic. If I think when we show that the chip can survive these 2 mole of sulfuric acid, well, we can at least go to the low, say we show that, or we see that it's stable up to a pH of almost 0. All right, so as I said already, we have the vanadium 4 plus, which has a spin of 1/2, and vanadium 2 plus, which has a spin of 1/2. So in these catholyte samples are stable in air, while the anolyte samples are unstable in air. This would call for in situ EPR, and that is planned also in the future, but currently we have only samples from the catholyte side. And this is how a sample, or how the spectra looked like. So when you just put them in a normal EPR spectrometer and quantify, like do a double integration, then you can get a linear relationship between the vanadium vanadium 4 plus, which would be the vanadilyl ion concentration and the intensity. So we use this proof of principle. We will use this as a proof of principle experiment for the quantitation of our EPR-on-a-chip in a harsh environment. And this is these are the data we got from an ex-situ experiment. So essentially we had a beaker when we had 6 solutions from 0 to 100% state of charge and 20% state of charge steps. And you can see the EPR-on-chip FM signal. So here at 0% state of charge, we have the most amount of the vanadilyl ion. So we have a concentration broadened spectrum. And when we go to 100%, there is no signal left, because there's a very small amount of vanadilyl ion left. So for comparison with like normal commercial EPR, we can transform this dispersion-like signal to an absorption-like signal. We're using Kramers-Kronig relation given if there's no saturation. And when you compare this to X-band data obtained with a Magnetech MS5000 spectrometer, we can see that the signal amplitudes have a similar ratio. And however, here at the 100% state of charge, we see a small signal, which is due to the fact that the Magnetech has a much larger sample volume to probe. The measurement time was 2,400 seconds and 1 nanoliter, as I said, of a sensitive volume versus 60 seconds and 50 microliter. Obviously, that is quite different. Here we take a few hours, and here it's just 1 minute. However, when we normalize the SNR values of the chip and of the expand spectrometer to the sample volume and to the time, we actually see that the absolute spin sensitivity, because this is what we then get, is up to approximately 500 times better than expand, and this is actually what we also get from estimating the or a similar value which we get from estimating the sensitivity from a theoretical basis. So when we then doubly integrate these two spectra to get the signal intensity, we get the same linear relationship for EPR-on-a-chip and expand quantitation. So we see that we could use this EPR-on-chip spectrometer. However, we need to improve the measurement time, and this is what I will show later. And but first of all, I want to show you one more spectrum. So we also simulated the catholite spectrum, this time with a, let's say, very narrow, with very not very low concentrated, at least in our opinion, for our samples, 0.16 mole, and measured this at X-band at 100 Kelvin to get the G&A tensor, and then we use the G&A tensor to simulate the spectra at X-band at room temperature and the chip, and we can simulate this with only one free fit parameter, and that is the rotational correlation time. And within the error, this is the same. So we see that the EPR-on-a-chip reproduces this vanadium spectra of resonator-based EPR. As I said, the measurement time is too long, at least for an application of this vanadium redox flow battery. So we did something very sensorish, I would say. We measured only at 2 points, so we had a very narrow spectrum, or very few points, just 2 points, 1 point on resonance slightly right of the second transition and 1 off resonance, and then we took the difference of the two, and we get a somewhat strictly monotonically decreasing function. So that would show, I think, with proper calibration, and maybe not exactly this value, we can get a somehow a 2-point you can use this 2-point measurement to reduce the measurement time and get still quantitative data. There's one other way. Obviously, we could also try to improve the sensitivity to reduce the measurement time and still obtain the whole spectrum. And there are 2 ways that we can use to improve the concentration sensitivity. And we call it the EPR-on-a-chip array. And the idea is to use not a single coil, but multiple VCOs, or multiple EPR-on-a-chips that are put together on one array, and they are intentionally injection locked, and then they are all they have a joint microwave phase. And when we then measure the global FM signal, and the sensitivity scales here with the number of coils to the 1/2, so square root of the number of coils, and that is what has recently been also experimentally verified, but this data is not published yet. Or the other way to improve the sensitivity in general is to use rapid scan EPR, and the idea of rapid scan EPR is that we essentially pass through the resonance faster with respect to the relaxation times T1 and T2, and we can accomplish that either by field or frequency sweeps, and detect the transient signal, and then essentially what we do, or what we can do is we essentially alter the saturation behavior from continuous wave to CRW. So here you have in black the continuous wave saturation behavior, and when we pass through resonance, we essentially increase the linear behavior to a higher B1, so we can essentially apply a higher B1 without saturating our sample, and that is particularly useful for long samples with long relaxation times. Samples with short relaxation times, such as the vanadium spectra, they are not so, they will not really benefit from that because they are not really saturatable anyway. And we tested these rapid scan capabilities of the EPR-on-a-chip, and this has been published a few years ago. And we did frequency swept AM detection. And the nice thing about the chip is actually that we can easily sweep the frequency, because usually you would sweep the field, the magnetic field, and maybe, as you can imagine, that sweeping a magnetic field at high frequencies and large widths is quite challenging. So, but we can essentially just simply sweep the frequency. And we tested these rapid scan experiments with a BDPA sample. And here on the right-hand side, you can see rapid scans transient. Since we used sinusoidal modulation or sinusoidal waveform, we pass resonance twice per complete sweep, essentially. And when what we see here on the trading edge of the signals are these wiggles. They are called wiggles, and in order to get rid of them, we need to use a technique called Fourier deconvolution. And when we did do this, we obtain the slow scan spectrum similar to what we would detect in CW. But this is 0th order. So what we found is that when we do rapid scan compared to CW with the same sample, we get an one order of magnitude improvement when we use rapid scan EPR compared to CW. On the bottom here, you can see the saturation behavior of the CW versus the rapid scan, and with increasing scan rates, so the shorter the time we spent on resonance, essentially the less saturation occurs at higher microwave fields. We also tested this for with a dipstick, and there we used the FM. We used FM detection, and this time we used again a 10 millimole tampon and water solution. And these experiments here were test experiments to see how much time we actually need to essentially reconstruct our signal with a good enough signal to noise so we can use it later. So here we get we have our EPR transient, a rapid scan transient. You can see small wiggles here, which were acquired for 16 minutes, and then we Fourier deconvolved that, and you see very nicely the 3 lines again. And this is the same sample, but only 30 seconds acquisition. And after deconvolution, you still get a decent spectrum. And this is towards a sensor-like applications where essentially the measurement time let's say the measurement per unit time is relevant. And we did also some oximetry, or we investigated some oximetry probe with this dipstick EPR-on-a-chip, and that is a turtle probe OX071. And that is the idea of these oximetry probes is that we essentially can determine the partial pressure of oxygen by you looking at the EPR spectrum, and that is useful for like clinical EPR. And the idea is that the line width of this probe is linearly dependent on the partial pressure of oxygen. This time we use the frequency swept FM detection, so dispersion-like spectrum, this FM spectrum. And here you see the continuous wave EPR spectra of this sample, once with oxygen present and once with nitrogen purged. Actually, this is the setup. The sample is in the beaker as shown before, and we put a nitrogen flow in this beaker, and then we measured while it was while the nitrogen was while it was nitrogen purged. You see from the CW spectrum that the SNR is very poor, but when we go to rapid scan, you can nicely see that the line width is narrow, or when the sample is purged, the line width is much more narrow than when oxygen is present. And for this certain application, the rapid scan technique really helps, because there in continuous wave we probably saturate our sample because the line widths are very, very narrow. Now I come to the permanent magnet development. This is I cannot really comment too much on that, because I was not so involved in this project, but I just want to show you what we have achieved in this. So Brucker has developed a single-sided permanent magnet, and that looks like that. The magnetic field is essentially parallel to the surface, or the most homogeneous region. This has a field strength of 250 millitesla and a homogeneity of 800 ppm, which is not very great, I have to say. But with this magnet, we can use this chip and have a free access from the top. So this is actually the whole setup. So the magnet is below here, and the chip essentially lies on the magnet, and this is a 7 gigahertz EPR-on, and here you can easily illuminate the sample or do whatever you like from the top. And on the right-hand side, we have an H-shaped permanent magnet, and that was developed by Stuttgart University. And I think it's quite cute because it looks like a tiny Brucker magnet, like a Brucker Helmholtz magnet. And this has a field strength of 500 millitesla, and the homogeneity is much better, or about an order of magnitude better. But due to this, like, it's better because we have these two coils essentially, but the access is rather limited. Again, so what do we need to get from that? We need to improve the homogeneity, but I think there are some nice magnets. So last point on my list is the determination of the sensitive volume, where I spent quite some time. So how do we determine the sensitive volume of such a chip? The idea, or what I did, is I used a chip, and I had a grain of BDPA which was put on a pulled capillary, on the tip of a pulled capillary, and then I essentially scanned I took EPR measurements, and at each point of my scanning of this small grain of BDPA, I took a spectrum, and then I determined the FM amplitude, the signal amplitude from that, and then this is what we get here from the signal amplitude. When we are, let's say, rather close to the chip, we get a signal amplitude which looks like I don't know, like a circular signal amplitude, and then we go away, and at a certain point we don't have a signal amplitude. What we see from when we fit these maps with a 2D Gaussian, then we get an asymmetric distribution of the signal amplitude. So it is larger in x direction, so in this direction, than in this direction. And that is decreasing when we move the sample away. From this measurements, we estimate the sensitive volume to be approximately 1 nanoliter, and we also mapped 3 coils, and here we used the EPR-on-a-chip array. So we had a global FM signal, and essentially when we have the sample placed in each of the coils, it doesn't really matter, because we will always get the same signal. So we can put the sample here or here or here, and we still get the same signal. So we were wondering, where does this asymmetry come from? And this can be explained actually rather nicely. So when we use these small resonators or small coils, obviously our B1 homogeneity is rather bad. So actually it's rather inhomogeneous. And so when we assume, when in the experiments, the B0 was along Y, and when we assume B1 to be made of only the component B1Z, which is perpendicular to B0 and perpendicular to the surface, so this would be this direction, we would get a circular shape of our signal amplitude. However, when we include our component, which is also perpendicular to the B0, that is the component along X, we get exactly this rectangle, this asymmetric shape, where in X direction we have a longer where it's asymmetric in X direction. It's rather like a flattened, like an ellipse. Okay, with that, I would like to summarize my talk. I showed you this that Parallel C codes like protects the proc innovate YP8 range actually from 7 to 0, and that we can do quantitative EPR-on-a-chip dipstick experiments in these very harsh acidic electrolyte solutions. And I showed you a few prototypes of permanent magnets for in situ operation. And I also showed you that the spectral shape can be, that we understand the spectral shape, that it can be reproduced, that we can quantify. I showed you an in situ EPR-on-a-chip dipstick experiment that was the oximetry, and that the lossy solvents seem to be of a minor problem. And maybe in the future, but I probably won't be there for much longer. We actually planned to do a combined or an online or operando state of charge measurement with the EPR-on-a-chip and UV-Vis in an actual vanadium redox flow batteries. And I need to acknowledge lots of people. Oh, there it is, and that is the group of Klaus Lips at EPR at HZB, Alexander Schnack's group at MPI CAC, Jens Anders group at the University of Stuttgart, and Klaus Peter Dinse for numerous contributions to for numerous contributions, and Peter Fischer, and obviously my funding agencies. And I'm happy to answer questions if you have any. Thank you.
Thank you for that very nice talk. The floor is open for questions from the audience. You can just unmute your mic and speak freely, or raise your hand if you feel like you need to do that. If your microphone's not working for any reason, feel free to throw your questions in the chat box. Mare.
So I had a question regarding homogeneity, because I think you pointed out rightly. So when you're doing frequency modulation, what is the frequency homogeneity that you sort of accomplish? And I think you showed the field homogeneity for the permanent magnet.
Yeah.
So what is your eventual goal in terms of homogeneity?
So you mean of the permanent magnets?
Both in terms of
Or,
frequency homogeneity, because to do a
I
good
mean,
ESR experiment, you need
yeah.
a
I mean, okay. So, the frequency. So the B1 has an inhomogeneity. The frequency is one frequency, though there's no homogeneity. B1 homogeneity obviously is a problem. However, only if we saturate our sample. So we see from the mapping that we see this inhomogeneity also in the spectra and from the asymmetry here. When we do not saturate, this will only give us different signal amplitudes. If we saturate, for instance, close to the trace of the coil, then we will get a broadening of the spectrum. So that is bad, but we can try to minimize saturation by using, for instance, rapid scan. There are other chips that were developed by actually the supervisor of Jens back like 10, 15 years ago, which have which can achieve much lower B1 that we have. So essentially we can then, which is like 10 or 20 times lower than we have. So there we can do, that we cannot reduce the B1 homogeneity, but we can reduce overall B1 and therefore make sure that we are not saturating. B0 homogeneity, as I said, there are certain ways to improve the homogeneity by placing some layers here. Actually, they put some. Now this is something I didn't really work on, so I cannot really say anything. So they put some layer. They produced at Brooker to that, and then we wanted to put another layer to improve the homogeneity of the field, which was which was supposed to be done by by a focused ion beam, like placing small magnetic parts, but this took a lot of time and didn't really work out in our project. However, since our sample volume is very small, the homogeneity is, let's say, not as the B0 homogeneity is not as problematic, I would say, as in, like, say, if you have a cavity where you have a very large sample where you have then
Yes.
yeah.
No, I agree with that aspect. The key is, of course, we have a smaller space for which we need field homogeneity with the ESR on chip. But I think it depends for the sample, what kind of samples do you detect? For example, in ESR at 10 to the power minus 6 is essential to get to a narrower sort of line shapes. Of course, for a broader line shape, you can have a less homogeneity.
Yeah.
Like in
Indeed.
NMR, you need 10 to the power minus 9.
Yeah.
So I agree with you that the volume or the area for which homogeneity is needed is much more smaller, so it's actually easier problem compared to the bigger spectrometer.
Yeah.
But I was thinking in terms of what kind of samples can we detect? Because if we go to say biological samples like COVID-19 samples,
Yeah.
it actually becomes a very interesting project for this
Mm.
thing. Is the homogeneity would be the limitation or not? That's
Yeah.
what.
I think for let's say lab applications, we can always use an electromagnet still. I mean, we did that, and there's no problem. We have these permanent magnets are rather for, I don't know, like in the field applications
Yes.
and not for lab applications. I mean, there are like small electromagnets which have a decent homogeneity. I mean, when you think of the Magnetech magnet, for instance, I think this has a rather it's not perfect homogeneity, but it's much better than what we have now. So if we could combine this, for instance, with this chip, this would also be okay, I guess.
And like if somebody else, I have few other questions, but I think I would like to give choice to somebody else.
There's a quick question in the chat. Why did you decide to put B0 in the plane of the coil and not perpendicular to the coil? But I think that's a slight misunderstanding, because the way the single-sided permanent magnet is oriented in the image, it looks like it's parallel to the oscillatory coil. But if you see the blue arrows, it's the field is actually perpendicular to the coil.
So there's the chip lies here, the B0, at least the B0 perpendicular to the surface of the chip is going upwards, and then we have obviously in X and Y also, or if we define this as that, we have an X and Y still B0.
Yeah, and you have a
B1.
Yeah, thanks for the nice talk. That's really nice what you guys can do. I was wondering, and then this is probably a very naive questions, but if you decrease the frequency, could you increase the size of your ring while keeping the same B1? And if this is true, what's the right trade-off between lowering the field and the frequency and having more volume?
Yeah. So thanks for this question. So we can go lower in frequency. I mean, you see here 7 gigahertz. It depends only on the design essentially of the chip. There's as far as I know, so there has been a publication recently where this coil, I will go back a little in the slides and then can see it, where this coil here actually was split up to be part of a segmented coil to go to much higher frequencies. The idea is that essentially you split that up to lower, or you do is like segment that to go to higher frequencies. You can do the same thing when you go down in frequency. So essentially we have then not one VCO per coil, but essentially multiple VCOs make up one coil. And with that, you can design essentially as large coils as you like, as long as you make the current that flows in the coil make their face such as if it would be one large coil. And this is, I think this has been published last year. And we like the people in Stuttgart developed this for 263 gigahertz. But you can do it also at low frequencies. And I think there's a 2 millimeter coil in the making, but I think I have no information about that, and I think I shouldn't talk about that.
Yeah. Okay.
Sorry, and did
Thanks.
you ask another question? Did I forget?
No, I was just thinking, well, because at the end, what you would like to have is increasing the active volume or the product volume, and that
Yeah.
I was just thinking
Yeah.
of.
So when there's this large coil, there's another publication where a hole was drilled inside the coil, and then you can still use the let's say small capillaries, which I mean it's nice for certain applications, but I mean when you think of this of the vision that you have a portable spectrometer doing that, putting then the tiny capillary in there is not so good. But in general, there's ways to go in higher in frequency, higher in diameter, and some of
There's
it
also the
published.
idea of increasing the number of coils.
Yeah, but
is that challenging to increase the size of your array? Could you make it 100 by 100 or something like this, or is that going to be too complicated?
No, I think like electronically it's not complicated, but it's just costly.
Okay.
These chips are produced in a CMOS on a CMOS wafer and you pay per size. So when you have a, let's say, 10 times larger area, you pay 10 times as much. And then at a certain time it's too expensive to produce very large arrays.
Okay, cool. Well, thank you very much.
Other questions for Silvio? Yuji, you have a question?
Hi, it's a very nice talk. I have a very simple question just to follow up about the inhomogeneity. So for the B1 inhomogeneity you had, so have you thought about optimizing the structure or the shape of the coil just to make it more homogeneous? Or just intuitively what kind of coil may provide a better homogeneity?
Yeah, I mean, generally, when you have planar micro oscillators or resonators, they are just by definition have an inhomogeneous B1. You can play a little bit with the design here, but however, when you miss the third dimension, you will never get a very homogeneous B1. So I think there's a paper by Jason Sidabras, and he used the micro helix to improve the homogeneity inside the helix. So essentially you can also do something like stack them together and make a hole in there, and then you have let's say stacked coils with a hole, and you can improve the homogeneity very nicely, I guess. But apart, like when we stay in this two-dimensional array, in the two dimensions, then there will always be inhomogeneity, especially perpendicular to the surface.
Okay, thank you.
Other questions?
If I can ask if everybody else have.
Feel free.
Sure, please.
No, it's actually a very nice project, and there are actually quite a few things that, as you may expect, that people will ask because it's a very exciting domain that you're working on. And so continuing from that inhomogeneity part, what UG previously, so what's the range? Like what's the foundations of inhomogeneity? Like have you estimated that part of thing or not? Like what's the boundaries of the inhomogeneity? Not the physical space, but in terms of actual values, like in terms of B1 values.
Yeah, we have simulations of the B1 values. Actually, I think I don't have them in this slide. So these simulations here, these are simulated signal amplitudes, and the B1 values we got were simulated with COMSOL. So we have the simulation of this array, and what we see here is when we are in the center so the ratio of the B1 here in the center, which is perpendicular to B0, and let's say here the maximum B1 is a factor of 5 approximately, and then it obviously drops. Like essentially, like when you do a simple calculation, you can use a current loop, a circular current loop, and use Biot-Savart law. You can find the equations on Wikipedia if you like, and just plot what you get, and within on the current loop, there's it's not defined on the current loop, but let's say within 10 microns of the current loop, inside you can estimate it very easily and very precisely. So when we have these B1 calculations, or the simulations from B1 by using this actual shape compared to the we find a good overlap with Biot-Savart's law. So yeah, factor 5, I would say, from the center here to the maximum B1, which is on this on the what is it called, on the conductor or inductor.
Nice. And now the next part, what's the step size of the frequency sweep? Like, what's the step size you're using for the sweep?
I mean, the step size. So we embed the dproc in a phase lock loop. So essentially, we control the frequency with a frequency generator, external one, and I would say it's as good as the frequency generator can provide. So hertz, or I mean, that is probably not so useful, but I mean, we here in these spectra, we had some kilohertz of step size.
Okay. So basically, you're sweeping at a kilohertz from X to Y, so I see 14.2 to 13.
Yeah.
So you're doing
and we modulate the frequency to get our phase sensitive detection. So we essentially we are here, we sit on this thing, and then we modulate with some kilohertz of modulation amplitude at 100 kilohertz or 80 or 50 kilohertz, and then we go to the next point, like in CW, but like in normal EPR, but with a microwave frequency instead of the field changed.
And can you extend to higher frequencies? Because this X band, I think, is still X band, right? 14 is still X band, or switches to KU band?
This is KU band. So the reason why it's at 14 gigahertz is that the first permanent magnets with a decent homogeneity that you can buy is 500 millitesla ones. So they bought them in Stuttgart or in Ulm at that time, and then try to optimize it. There has been so we have chips there are chips, I think, from 2 gigahertz, 7 gigahertz, 14, 28 gigahertz, and then up to 263 gigahertz. And actually, you can use, and there's one chip which oscillates at like 90 something gigahertz, and that when you use higher orders of the oscillations, you can go up to 360 gigahertz. That is all published already. All these up to 360 gigahertz.
But you need the field, so either you could.
Yes, I mean, permanent magnets can deliver maybe 1.5 Tesla. You need obviously a magnet, a proper magnet then.
So there's another question in the chat. Can you analyze a solid material placed on the surface of the chip? And if so, what's the penetration depth of the EPR signal within the material?
Yeah. So yes, we did that. I also don't have it here. I have to say I'm very badly prepared today. I analyzed, or maybe I can give me 1 second, then I can show you some data on that. On a thin, like rather thin film. Let's take these slides. We analyzed, or I have a thin film sample of amorphous silicon on quartz, and this amorphous silicon is like 15 micron thick. Let's see if it's in here. Guess it is. And I did a similar experiment to the mapping experiment. Yeah, here. And that was removing the sample. So this is the sample here, 50 micron amorphous silicon, not hydrogenated or anything. It's just e-beam evaporated amorphous silicon on quartz glass. And then this was covering all 12 coils, and I removed it from the chip. And here you see the signal amplitude versus the distance of this amorphous silicon sample, and you can see after like 100 micron, there's no signal left, or very very tiny signal. So with this amorphous silicon, I would say we have the penetration depth. I mean, like the sensitive height of 100 micrometer. Similar for the BDPA sample.
Okay, other questions from the audience? I don't see any more hands. If not, maybe now is a good time to stop. So I will say thank you to Silvio once again for the very nice and in-depth presentation, especially during the questions. And thank you all for your attention. And we'll be back in 2 weeks for our next presentation. I wish you all a wonderful rest of your day, wherever you are in the world. Maybe evening, maybe morning, but enjoy, and we'll see you all next time.
Bye-bye. Thank you for listening.
And I am now, unfortunately, to my next meeting, so I have to run, but see you all.
Bye.
Bye, Joe.
Bye.
Yeah.
All right, thanks,
Do you have
Silvio,
some-
for
Okay,
the
yes, thank you. Sorry, I
presentation.
needed to close my
Yeah.
virtual machine. So,
Bye.
okay, thanks for letting me present. Bye-bye.
Sure.
Have a nice
Thank
day.
you.
Bye-bye.
Bye.
Hi, Eugene. So,
Do you have some questions?
yeah, so first, concerning the last seminar from Bela Bode, are we allowed to publish it on YouTube?
I don't know. I was away last time, so I didn't.
Okay. You didn't discuss because I forgot to ask him.
Right. Okay. I can send him a message just to ask
Okay,
very quickly.
thanks. And the
Okay.
second thing, if you have a second, I have just a trivial
And
question.
Graham, obviously, he's still preparing his recording, so it will take a bit longer, I think.
Yeah, I completely forgot about that. I have a short question about the B1
Yeah.
simulations you have in your paper.
Mhm.
Just share it quickly. It's just a trivial question.
Yeah.
Mostly it's just technical. Let's see.
Very happy somebody is actually reading the paper.
It's in the SI. You have this plot here.
Uh-huh.
So this you did it with CST, I guess, right?
Yes.
So you basically what is this? Is the absolute magnitude is of the H field, or is in every 3 directions?
For this one, I think it is the absolute H1 field in the direction we want for the magnetic resonance.
So only
So there are 3 components, and we have one of them. Yeah.
only one?
Yeah.
But because in the plane you would have 2, right? You would have like I think your tube is kind of standing vertically in the magnetic field, right?
That is right. Yes.
So maybe you calculated the
Yeah,
max, the absolute. I don't know.
No. Sorry. So this is the magnetic field. Removed the longitudinal magnetic
The
field.
longitudinal.
Yeah. So
okay.
it's the in-plane one. Yeah.
In plane. So you have the 2
Yeah.
directions. Okay. So and then I'm wondering, what do you have on the y-axis? Is called beam counts, and then how did you get that out from CST? Because like when we do that, like we get percentages.
Yes. So sorry, probably I should plot it in a better way. the way CST works is it calculated the mesh units.
Yeah.
So it divides your sample holder into very small units and then derive the Maxwell equation and so on, solve the
Okay.
magnetic field inside it. And then when I try to export the magnetic field distribution, so I could set a step interval and then chop the sample volume into this step interval units.
Yeah.
If that makes sense. And then in total there will be millions of cells I will be looking at, and then
Exactly.
this is basically the distribution.
Okay, so basically, so you got this plot using the function field statistics or not, or something else?
Can you repeat again?
So you got this plot using the field statistics export function or something else?
Yes, it's I think
The field statistics or no?
I think it's when after the simulation, so it shows a animation how the magnetic field will change, and then I pick the moment that the phase that gives the largest magnetic field in the sample, if that makes sense, and then I export it as a 3D
okay.
TXT
Got
file or
Okay, got it. Yeah. All right. That makes
probably
sense.
I should add more about how I get the data.
No, it's fine. It's fine. It's just a detail. It's just a very minor detail.
Yeah.
And you didn't do any analysis on this plot, like you didn't extract any average or anything, right?
I did calculate average. I think the average B1 field is like 15 Gauss.
Okay, so it's the one in the paper then. Okay.
Yeah.
In the main text, right? Okay.
Yeah.
All right. Cool. Thank you.
Okay, no worries.
All right. Yeah, we stay in touch for this for the next seminars, I guess.
Yep.
All right. Good luck with your visa.
Okay, thank you. See you in 2 weeks time.
Yeah. Bye-bye.
Bye.